So today's our second to last lecture. We are going to be talking about a little bit of imitation learning and then a bunch of RL, right? And so let's get started. Um, so we talked about this formalism for sequential decision making through a Markov decision process, right? So an agent observes the world, sees a state, decides to take an action. The action transitions the world to a new state, providing the agent a reward R in the process. Your goal is to learn a rule that decides what action to take in every state. So you're trying to learn the parameters of your policy pi theta that takes in a state, gives you an action, and the goal is to maximize the expected sum of rewards, right? And so almost all decision-making problems take this kind of form. We said there were three different ways we could try and solve this problem. We have model-free RL, which we'll try to cover today, model-based RL, which we'll hopefully cover on Wednesday, and imitation learning, which we covered last time, right? And so we started with imitation learning, and imitation learning is very, very simple. It says, let's take a data set of states and actions that are considered to be close to optimal, right? And let's just pretend that they were expert and treat this as a supervised learning problem, right? So we're going to take states and actions, mix them up into a data set, treat them as IID samples, and then do maximum likelihood, which means we're going to try and get a policy pi theta, which maximizes the likelihood of the action A star being produced at a state S star, right? And so this is all of what you think of in machine learning. When you think of supervised learning or regression or classification, like they're all kind of the same maximum likelihood problem, right? And so the code looks something like this. Essentially, it's just like the standard PyTorch loop for doing supervised learning. You're trying to get the log likelihood, take its negative, and minimize the negative log likelihood or maximize the likelihood. And so that's what imitation learning through behavior cloning is, right? And we saw that there's some problems with this approach. The issue is that you're trying to treat this as a supervised learning problem, but it's not a supervised learning problem, right? So it's essentially a sequential decision-making problem, but you're treating it like a supervised learning problem. So you're ignoring the sequential nature of the problem. And that leads to this compounding error issue. So you make a little bit of a mistake, you make a bigger mistake, a bigger mistake, a bigger mistake, and then you keep going further and further off the rails, right? And so the issue with behavior cloning is that you're making small mistakes, which wouldn't matter so much in a one-step problem, but in a k-step problem, those errors compound, right? So you go a little bit out of distribution, gets worse and worse and worse. And so that's kind of the one of the big issues in imitation learning, right? And so we talked about a few ways to deal with it. Um, the key idea in all of these is that you want to kind of come back to the manifold of things that you know, right? Or things that are good, right? And so all of them are essentially trying to make you stable, as in they're trying to like bring you back from out of distribution states to in distribution states in some way or the other. The first method we talked about was a method called Dagger or dataset aggregation. Right? And dataset aggregation just says, well, you do behavior cloning, you run your policy, you see what states you visited, and on those states that you visited, you then have an expert label what the expert actions would be, right? And so you like start, you run your policy, you get the observations, you ask an expert to label them, you aggregate that data set with your previous data set and repeat, right? And so essentially what it's trying to do is trying to make the supervised learning problem closer to a sequential decision-making problem, right? And so it's trying to bridge the gap between supervised learning and sequential decision-making. And so we said, okay, that Dagger is great. It kind of works, but there's some issues with it. The first one is that you have to do this thing after the fact. So you have to like first run the policy and then get someone to label actions after the fact. But if you like ask someone to like look at images and kind of label what the optimal actions are, that's not always easy to do, right? And so the first thing that we said we were going to do was try to get corrective data during data collection rather than after, right? And so this first idea called DART says that we're going to just take the expert data, add some noise to it, and have a human serve to correct that data, right? During data collection time. And so you in imitation learning, you'd get narrow data like this. When you do DART, you get like a broad data coverage like this, each of which brings you back to the correct manifold, right? So all you need to do is add a bit of data, add a bit of noise during data collection, and have a human kind of correct for it, right? That's the first technique we talked about, but that's not always possible. And so we talked about a second technique called CCIL, and the idea of CCIL is you're going to try and get corrective labels that look something like this, right? On the bottom. And you're going to get those corrective labels by having a model of the world. So you're going to figure out how the world works, an approximate model of the world, and then use that to generate synthetic labels that bring you back in distribution, right? The problem with this is that your model of the world may not be accurate everywhere, so you have to be a little careful where you're generating these labels. So this is a recap of what we did last time, right? So that's kind of what we talked about with imitation learning so far. Any questions? Okay. So the second issue that often comes up is an issue called multimodality, right? And so the issue is perhaps best exemplified by this example, right? So imagine you're at a tree, you're a drone. Sometimes the drone goes left, sometimes the drone goes right. Right? So some experts decide to take you left, some experts decide to take you right. And then you try to do imitation learning with it, right? And let's say you had like a Gaussian policy and you're going to do regression, right? So you're going to do maximum likelihood with your policy class being a Gaussian. What's going to happen in this case? So your policy is a Gaussian, which means that your policy is unimodal, right? Um, and your data distribution has 50% going left and 50% going right. What's going to happen? Yeah. You end up going into the tree, right? So basically what happens is that you kind of learn to average these two modes. So you have like a bimodal data distribution. The best fit with imitation learning will be something like this, which sends you like straight through the tree, right? And so there's often an issue of multimodal data being underfit with a non-expressive probability distribution, which is going to send you, you're going to average the modes and send you right into the tree or the cone here, right? And so remember, it's not that your neural net wasn't big enough. It's not that your function approximator wasn't powerful enough. It's that you're trying to fit a non-Gaussian distribution with a Gaussian, right? If you have something that's 50% left and 50% right, there's no way it can be a Gaussian. And so there's like a mismatch between the distribution that the expert actually had and the distribution you're trying to fit, right? And so this is often what you call the multimodality problem, right, in imitation learning. And it often leads to catastrophic failures, especially because humans are inherently very multimodal, especially when you have a mixture of humans. And even without a mixture, like when you do things yourself, you'd often do things slightly differently. So it's about distributional expressivity, not about network size, right? So don't just make your networks bigger. It's not going to fix it. Um, so how do we fix it? Well, we can use more expressive probability distributions. Any ideas what these might be? We want to use a probability distribution that can fit like multimodal data. So we know that a Gaussian is just unimodal, so it can't really fit it. If we had to use a different probability distribution, what would we use? In the news or from, let's think about different scenario, right? Let's think about generative modeling for images. Images are inherently multimodal. You like ask someone to generate a picture of a cat, it'll generate 100 different pictures of cats, right? And so those data distributions are inherently multimodal. And so if you think about, your favorite mid-journey or whatever, stable diffusion or something, like what kinds of probability distributions did they use there? Do you guys know? Any ideas? No? Okay. Um, well, there's a bunch of things you could do, right? So there's, for instance, a bunch of these different options, right? So you could um, start the first one, which is the easiest, is to go from a Gaussian to a mixture of Gaussians. And so you can kind of think of a Gaussian in 2D as this. You got to think of a mixture of Gaussians in 2D as this, right? So it's a combination of many different Gaussians, right? A latent variable model is a model that it's like if you've seen a variational autoencoder, if you heard of variational autoencoders, they're functions that like basically take in a latent variable or which is sampled from a probability distribution and produce like a multimodal distribution with it. Autoregressive discretization is a way to try and convert these continuous distributions into discrete distributions that are multimodal by construction. And diffusion models is the one you probably heard of, which is trying to like model distributions with iterative changes, right? And so we'll go over a few of these, right? But yeah. Um, so diffusion models are interesting because what they try to do is they they try to like have a like normally what you do is you have to construct this thing and back propagate through it through auto differentiation. What diffusion models essentially try to do is they try to like not fit p theta. They instead try to fit this thing called the score function. And the score function is the gradient of the probability distribution. And so what they do is they try to fit this thing, which is like S, they call it S theta X, right? And they're trying to fit the gradient of the probability distribution. And they just treat that as a vector, right? And so the gradient of the probability distribution can be a vector because it doesn't need to be normalized. And so it's not fitting any particular family. It's saying that it's an expressive uh, distribution class that can fit anything whose gradient can be modeled. Right. And so the change in diffusion modeling is rather than trying to choose a particular class for this, you instead try to directly model the gradient, and that gradient doesn't prescribe what class P has to be. So yeah, it's an interesting, it's I like there's many different interpretations of diffusion models. I like the score function interpretation better because it like makes intuitive sense. Like the version you'll see often is this like you go from image to noise and noise back to image, but that doesn't really explain what probability distribution it's looking at. Good question. So let's go through a few of these, right? So the simplest one is a mixture of Gaussians. And so a mixture of Gaussians just says that your probability distribution is the sum over k different Gaussians, each of which are weighted by some function wi, right? And wi is like something that sums up to one, right? So you say wi over I sums up to one. So you can kind of think of it as like you take a bunch of different Gaussians and you kind of average them together, right? And so what that essentially means is that your probability distribution goes from being this to something which looks like this, right? And why is this not always what we use? Like what might make this hard, do you think? So this is good because if you want to model more complicated distributions, you just increase the number of Gaussians, right? But what might make this hard to use? Yeah, so I think basically it gets harder and harder to optimize as you have more and more Gaussians, and it's not always clear how many Gaussians you want to have, right? And so that's kind of what makes it hard to use. And empirically, people find that it just doesn't work as well. But it's the easiest thing to try. The other pretty popular one is diffusion models. And so one of the papers that are in the CETA discussion for this week are diffusion policies, which try to essentially model um, grad log phi of A given S, right? And so they're essentially trying to model the score function. Rather than trying to model pi of A given S, they're trying to model this gradient. And then they use like a diffusion process to sample actions. And that lets them sample pretty multimodal actions. So if you look at these examples, let's see that. Um, you can see that they're, let's see, do they have visualizations here? Yeah. So you can see the diffusion process here. It goes from noise to samples, right? So you can see that you start from a noisy thing, you come back into samples, you start from a noisy thing, you come back into samples, right? And so it lets you be pretty multimodal, and that lets you do a lot better empirically when you have human data, right? Um, we won't have enough time to get into the rest, but it's a rich field. We'll hopefully discuss it a bit on Friday, right? Okay. And so some cool videos. These are actually a year old. The latest videos are actually cooler. But this is from 1X, which is a startup out of the Bay. And they're trying to put these robots in people's homes. They now have legs. And they showed up on like a cooking show. Um, and they're shipping to people's homes now. So it's getting eerily real. But most of this is actually done with just imitation learning. So they collect large amounts of data and do large scale imitation learning. And it works surprisingly well. Um, Another one, which is from a more academic institution, is this one from Stanford. called a mobile aloha. So they have someone just kind of teleoperating a system, collect a bunch of data, cooking shrimp, and then they like are able to like generalize to new scenarios, and be autonomously like navigating around the building and so on. And just with imitation learning mostly. Um, and lastly, this is one from Toyota Research where they're doing these diffusion policies. And you can see that they're doing like pretty cool tasks like spreading peanut butter and um, picking up grapes and like whisking things using tools. Things that seem really, really hard for model-based control often become a lot easier with imitation learning. So here they have an example where they're like using tactile sensors. That big bubble is a tactile sensor. And so imitation learning is really, really simple and really, really scalable, but it has some fundamental issues like we talked about, right? And so it's not the final answer, but it's a big step. And so the demonstration process looks something like this. Um, Sweet. Okay, so a little bit of perspective on imitation learning before we go to RL. What are you doing on time? It's nice because it's easy to use. You don't need a lot of additional infrastructure. Um, and it can be sometimes be super duper effective, way more than you thought, or way more than I thought. Um, but the cons are that there's inherently a challenge of compounding error. Doesn't really teach you how to recover or get better if you fail, right? Doesn't really generalize as far as I can tell. Like you can copy things in your training set. I haven't seen it really generalize. And it's really expensive in terms of data collection. So if you have millions of dollars, then it's doable, but otherwise it becomes hard to really scale, right? Um, okay, so that's imitation learning. Any questions about imitation learning before we keep going? No? Okay, good. Alrighty. So let's talk about RL, right? So RL is all the rage. You guys heard of DeepSeek, and RLHF and all of this stuff. Like all of it is using essentially model-free RL that we'll talk about today. It's not very, very complicated. Um, but the idea behind reinforcement learning is that rather than trying to learn from an expert, let's learn through trial and error, right? Especially model-free RL is just trying to optimize this objective through trial and error, right? So it's going to say, let's take this objective, let's try to do gradient ascent on it, and the resulting algorithm will look like trial and error. And most model-free RL is essentially try a bunch of stuff, see which stuff is good, do more of the good stuff, do less of the bad stuff, right? That's the key idea. It's very simple. Okay, so let's go back to our objective. We're going to do a bunch of whiteboard stuff today, but um, we're going to take our objective, which is the expected sum of rewards. Okay. I'm going to use R tau as a shorthand for the sum of rewards this way, right? Which means that this objective can be written as expectation tau coming from P theta tau, which is the distribution of trajectories under your policy in your environment, right? And R tau is going to be the reward of your trajectory. So you can kind of think of this as you draw trajectories from your policy in your environment, you compute the reward of each of those trajectories, and then you average it, right? And so that's essentially what the expected reward is. Okay? Written another way, whenever you have expectation P of x, f of x, right? You can always write it as integral P of x, f of x, dx. That's just the definition of expectation, right? And so the expectation we're going to write here is if you convert this into integral form, you get this guy. You get integral P theta tau, R tau d tau. And reinforcement learning is just going to be gradient descent on this. Just do stochastic gradient descent, and it's going to give us our fancy algorithm, right? And so we'll work through that. But the key idea at most of RL is we're going to try and do gradient descent on this objective. It's going to give us, a problem that looks like this. If I can compute the gradient of this objective with respect to theta, then I can do ascent on it, right? But if you look at normal problems, right? So if you look at problems like we did in behavior cloning, they look a little different. And the difference is a little subtle, right? So in behavior cloning, what you often have is that if you remember what we did, we said S star and A star come from your data set, and then you maximize log pi theta of A star given S star, right? So if you look at this, the theta is inside the expectation, right? So if you look at the objective in supervised learning, the theta is inside the expectation. If you look at the objective in RL, you have trajectories from pi theta or p theta r tau. So you can see that the theta is the like variable you're doing expectation with respect to. So theta parameter is the probability distribution, not the thing inside, right? And so the nice thing about it is when you have like the theta inside and you take the gradient, you can just pass the gradient all the way inside. And it's easy to compute, right? So the gradient of this objective with respect to theta is essentially expectation SNA from D grad log pi theta A star given S star, right? You can just like push whenever you have the expectation does not depend on theta, you just push the gradient all the way inside. And so it's easy to compute because you can just do stochastic gradient descent. That's what all of PyTorch, etc. does, right? Easy to do. Now the problem with this guy is you can't just take the theta and push this inside because the thing that depends on theta is the expectation variable, right? And so that's what's going to make this complicated. So the difference between supervised learning and reinforcement learning is that one of them has theta in the expectation where it has the like theta in the probability distribution. The other one has theta inside the expectation, right? And so like the important thing we've got to do is figure out how to take the gradient with respect to the probability distribution. Yeah. Okay. So we're going to try and work through that, and that's going to give us our RL algorithm. So you all can help me work through this, right? So we have this thing j theta, which is our objective. Our goal is to compute the gradient with respect to theta of j of theta. Right? We're just gonna like do some multivariable calculus. Okay, so if I'm going to compute this gradient, um, someone tell me what the next step is going to be. So I've taken the gradient is outside. What do I do next? How do I simplify it? Sorry. So okay, so we have this grad theta outside. How am I going to simplify this? You guys have done calculus, right? So there's a gradient of an integral. Yeah, what happened? No, it's not that complicated yet. All you're just going to do is you're going to just move the gradient inside. Yeah, you're just going to move the gradient inside. So the first thing we're going to do is move the gradient inside, right? And r tau is a constant with respect to theta. Only thing that depends on theta is p theta tau, right? And so this gradient is only going to hit p theta tau, right? So it's integral grad theta p theta tau r tau d tau. Okay, so this is great. We can actually compute grad theta p theta tau. The difficult part is that we don't know how to compute this integral, right? So if you ever have an integral, it's like hard to compute an integral over all things, but if you have an integral with a probability distribution, right? You can write this as an expectation p of x, f of x, right? And the nice thing about an expectation is you can compute it through samples. You can just take a bunch of samples and average them. And this is what we talked about Monte Carlo estimation earlier this quarter, right? So if you ever have an integral that looks like this, where one of the terms is a probability distribution, then it's nice because you can compute it with samples, right? So we're going to try and convert this thing, which is not of that form, into something that is of this form so that we can compute it with samples. And so the problem with this thing is that it's great, but there's no probability distribution here. There's only gradient of a probability distribution, which you can't compute with samples. Right? And so we're gonna change this a little bit. So I want to remember I want to convert it into a form that looks like p of x fx dx, right? Where p is a probability distribution and f is anything. So I want to convert this into that. What could I do?
The left side of you can, I guess, multiply and divide by that.
Perfect. Yeah, you got it. So you just multiply and divide, right? So you just multiply and divide by p theta tau. Like Devin just said, it's just one, right? So you multiply and divide. And the nice thing is now you can group this whole thing as your f, this as your p, this as your dx. And now you're nicely in the form of integral p of x, f of x, dx, right? So this is nice because I can compute it with samples. So let's try to do a little bit of simplification, right? So um, if you like group these terms together, if you group these terms together, then these terms, you can write this as grad theta p theta tau divided by p theta tau, or tau, right? But if you use the chain rule on like grad theta of log p theta tau, by using the chain rule on this, right? So what you can write this as is the derivative of log p theta tau with respect to p theta tau times the derivative of p theta tau with respect to theta, right? Just the chain rule of calculus. And so this thing is 1 over p theta tau, and this thing is the gradient of p theta tau, right? So the chain rule tells us that the gradient of log p theta tau is exactly equal to this thing, right? So the chain rule tells us that grad theta log p theta tau is equal to 1 over p theta tau times gradient p theta tau. So the chain rule, this will be the first term, this will be the second term in your chain. And so what that allows us to do is it allows us to simplify this expression to grad log p theta tau. Yeah. So all we did, let's recap, right? We moved the gradient inside, right? Then we multiplied and divided, and then we like grouped these two terms together, and we noticed that those two terms together are just grad log p theta tau. And so now your expression simplifies to something really simple. The expression just simplifies to p theta tau grad log p theta tau times r tau t tau. Tau is the trajectory, right? And so this is nice because I can rewrite this as an expectation. I can say this is an expectation. It's the expectation of trajectories drawn from p theta tau, grad log p theta tau, r tau. And so this is nice because it's like you can compute this with samples. Like you just need samples from your environment. You need to be able to compute grad theta log p theta tau, which we'll talk about in a second. And then you weight it by r tau, right? So, but intuitively, this makes a lot of sense. It says draw a bunch of trajectories from your current policy. Decide which ones have high reward and low reward. Take the things that have high reward, increase their likelihood. Take the things that have low reward, decrease their likelihood. And so you can kind of think of this as move in the direction of increasing likelihood. And it says increase the likelihood more for things that have higher reward and decrease the likelihood for things that have lower reward. And so it's basically instantiating trial and error. It's saying sample a bunch of stuff and then weight it by R and increase the weight of good things and decrease the weight of bad things and then resample. That's it. That makes sense intuitively, right? So all we did is we took our objective, we took our gradient, we moved the gradient inside, multiplied, divided, used the chain rule, and then we get an expectation again. Expectation is something you can compute with samples. And so it's often called the reinforced trick. It's behind PPO and policy gradient and all of GRPO and DeepSeek, all of them basically use this trick somewhere in there. But that's the key idea. Any questions? Does it make sense? Okay, we'll go over some more intuition in a second, but this is still not something that we can implement in code, right? It's still a little abstract. DAOs are a little abstract. So let's kind of simplify this p theta tau a little bit. Right, so if you think of any p theta tau, a p theta tau is basically the likelihood of a trajectory. And the likelihood of a trajectory is the likelihood of the initial state times the likelihood of your initial action times the likelihood of the transition dynamics. So you can think of the likelihood of a trajectory as the likelihood of S naught times the likelihood of the first action being taken at S naught by your policy times the likelihood of the environment transitioning to state S1 times the likelihood of A1 being taken at S1 times the likelihood of transitioning to S2 and so on. Right? So you can kind of think of this as like you sample the first state and you sample the first action then you sample the next state, then you sample the next action, then you sample the next state, then you sample the next action. Right? So if you want to, it's like you're trying to get the likelihood of a chain, right? And the chain has the Markov property. So the chain is the Markov property. You can kind of break it up into the likelihood of your first state, first action, next state, next action, next state, next action. So, right? And so you can always write the likelihood of a trajectory as a product of your initial state times the policy by theta, and your dynamics. You have ST plus 1 given ST and AT. Right? And so you can always write it as this product. So the nice thing is that when you substitute this into the previous expression, you can write log of a product of things is the sum of the logs of them. Right? So you have a log of the product of these three things. It becomes log P of S naught plus the sum of log P ST plus 1 given ST and AT, which is dynamics, and log pi theta AT given ST. Right? So you just did log on this product. It became sum of logs. And now you can go and substitute this back into your expression, right? So you wanted to get grad log P. If you remember the previous expression, we had grad log P, right? And so if you want to compute grad log P, take this thing, compute the gradient with respect to theta, right? Now, what are these two terms? Like, what is this term and this term? If you're taking the gradient, theta is only the policy. The only thing you can control in the environment is the policy, right? So you can't control the initial state distribution. You can't control the dynamics. And so what are these gradients? 0, right? So the gradients here are 0 and 0, right? And so this basically simplifies out to grad log p theta tau simplifies out to the sum over time steps of grad theta log pi theta at given st, right? And notice that this is just your policy. Like your policy is just completely under your control. So that's why it's called model free, is because you never need to know the dynamics. The dynamics totally cancel out, right? The only thing you need to know is your own policy, right? So this is called model free reinforcement learning because you never need to know the dynamics of the world. You just need to be able to sample from it. So it's going to make a little more sense when we put these pieces together. But the overall objective for reinforcement learning looks something like this, right? You start from taking the gradient of the expected sum of rewards, right? So we started from the gradient of the expected sum of rewards. We simplified it down to this expression, right? Which is expectation of grad log p tau times r tau under your policy distribution. Then we like expanded what p theta tau was, and we saw when you take the gradient, the dynamics totally cancel out, right? And so you can finally simplify your expression into something that looks like this. You can say if the expectation of trajectory is drawn for p theta tau of grad theta log p theta tau times the sum of rewards, right? And then if you simplify it more based on what we did in the last slide, you can say it's you sample trajectories under your policy and your dynamics, and then you increase the likelihood of things that have high reward, and you decrease the likelihood of things that have low reward, right? So you're saying take actions and states for trajectories that have high reward and increase their likelihood. Take actions and states for trajectories that have low reward and decrease their likelihood. And so essentially you can then there's an expectation, so you can approximate it with samples. And so this is something you can implement in PyTorch. You just draw a bunch of samples, you compute grad log pi, you weight it by the rewards, and you increase likelihood for good trajectories and decrease them for bad. That's it. But nowhere do you need to know the dynamics of the world. You just need to be able to sample from it, which means you need to execute trials in the world, but you never need to know how the world works, right? You kind of like learn that implicitly, but you never need to know how the world works. So intuitively, you can kind of think of it this way. You like sample a bunch of actions, you see which things were good, see which things were bad, increase the likelihood of the good stuff and decrease the likelihood of the bad stuff. And so if you had a bunch of trajectories, one had reward 30, one had reward 100, one had reward minus 10, right? You're going to really increase the likelihood of these actions at these states, increase that likelihood of these actions at these states a little bit, and then decrease the likelihood of these actions at these states, right? And so that's kind of how it looks. So this is what you call policy gradient, right? So it's policy gradient because you took the reinforcement learning objective, you just took gradient ascent on it, and you just did a little bit of manipulation The only reason you had to do the manipulation was because um, your your objective had the p theta inside the expectation variable, not inside the not it's like or your theta was the thing that you're taking expectation with respect to, not the variable that you're inside the expectation, right? So supervised learning, you just pass the theta all the way in. In RL, you can't pass the theta all the way in. Right? That's why you had to do all of this multiply, divide, and all of this fancy stuff. But the nice part is that it comes out to something that looks a lot like supervised learning, but it's weighting supervised learning with rewards, right? And so the important part is that you're not just doing supervised learning with a stationary data set. You're saying that I can learn from suboptimal data too. I just need to be able to weight things by how good those trajectories were. Okay. So the resulting algorithm essentially goes like this. You collect a bunch of data. You then compute the gradient that looks something like this, right? So you collect a bunch of data on your robot. You compute the gradient by basically taking the sum of grad log pi, weighting it by the sum of rewards in a trajectory, right? Then you take a gradient step on your policy. You get a new policy. Then you sample a bunch of new trajectories from that new policy, and then you repeat, right? So you go through this like data collection, policy update, data collection, policy update loop. And so unlike supervised learning, in reinforcement learning, your data set is changing all the time. There's no stationary data set. Your data set is changing every iteration. In policy gradient, you don't have any stationary data set. Your data set is different every time. And so if you ever do like PPO, you often have huge batch sizes because you need to like collect a lot of data every time to construct this gradient. Yep. Okay, and it's also called an on-policy algorithm because you have to sample from your current policy, right? So if you look at this algorithm, you're sampling from your current policy. You take your current strategy, your current policy, and you're sampling a bunch from it. You're running it in the world. You're computing the gradient from those samples that you just took. And then to do the next gradient step, you have to take samples again, right? Because if you look at this expectation is under your current policy. It's under your current policy, which means that every time you have to compute this expectation, you have to take samples from your current policy, which is why you need so many trials, right? Like you try something, you take a step, and then you try something again, right? And so that's why it's an on-policy algorithm. Okay, so that's reinforce. And so the pseudocode is a little bit dense, but it's like actually really easy. All you're going to do here is you're going to like essentially um, I just did it to indicate how simple it actually is, right? It's basically saying you feed in your states, right? And then you say, I'm going to compute the likelihood of a Gaussian, right? So you're going to feed in your states, predict the mean and covariance, compute the likelihood of a Gaussian, multiply those likelihoods by the rewards, and then take the negative of that thing and minimize it, right? Which means you're going to try and maximize the likelihood times reward, right? So there's like 5 lines of code to actually implement. All you need to do is get the likelihood of an action at a state weighted by the sum of rewards, and then like maximize that. Okay. You can also do this with discrete actions. It's not that different. All you need to do is change the Gaussian likelihood with the cross entropy, right? So cross entropy is basically the likelihood under a multinomial distribution. And so you can do exactly the same thing that you did. So if you do classification, right? If you do like multi-class classification, you essentially just optimize this negative log likelihood. All you're going to do here is you're going to like multiply your negative log likelihood with your rewards. And that's it, right? And so that's going to be the whole thing. Okay, so the way this is related to supervised learning is that in supervised learning, you compute the grad log p. In RL, you compute the grad log pi, and you weight it by the sum of rewards. Right? But there's a few things that are super different. The first thing is that it's inherently sequential. Right? RL is inherently sequential. So like whenever you weight grad log pi, you're not just weighting it by the rewards now, you're weighting it by all of the rewards in the future. Right? So what that means is that your actions will not just affect you now, it'll also affect what happens in the future. Right? So that's why it's sequential. And so if you look at this weighting function, it's including all of the time steps. Right? And so unlike supervised learning, which is just a one-step problem, RL is inherently a multi-step problem. The second thing that's different is that your data set here is going to be changing every time. Your data set here is static. Right? And so these are like, they look very similar, but they're kind of different. Um, okay, but essentially you can kind of think of it as like policy gradient is selecting good data and then increasing the likelihood of the selected data and then sampling more trajectories around the good data. Right? So it's like good data, do more of it and sample around it, and you keep repeating this until convergence. Okay, so that's policy gradient. Let's kind of recap it. I know there's a lot for like 20 minutes. We started with the objective. The objective was the expected sum of rewards. The issue is we couldn't take the gradient because p theta was inside the probability distribution. Instead, we did this like reinforced trick, which is essentially multiply and divide, and then use the chain rule, right? And the chain rule just like simplifies to this thingy. The nice thing about doing it this way is that it becomes an expectation. An expectation can be computed through samples. We then simplified what grad log p theta tau was because we can't change the dynamics of the world. We can't change the initial states. We can only affect the policy. This is what makes it a model-free algorithm, right? You never need to know P at all. You never need to know the dynamics. And so that you can simplify to an expression that looks like this. The expression just says, take all the likelihoods of actions at states in the trajectory and increase them according to the sum of rewards in the trajectory. Right? So the important bit is that it is the sum of rewards in the whole trajectory, which means that it takes the whole sequence into account. Right? And then this is something you can implement with samples. And intuitively just increase the likelihood of good stuff and decrease the likelihood of bad stuff, but you're doing this repeatedly. You're never just being stationary, right? And so that's policy gradient. Any questions? Does this totally make sense? Ish? Or is it so bizarre that none of it makes sense? Yeah. Yeah. So the way that you can, this is probably the easiest expression to look at. So the way you'd actually compute this in practice is you're going to sample a trajectory, right? So you're going to say, I'm going to sample my initial state. I'm going to sample my initial state from my initial state distribution. I'm going to sample an action from my policy. Then I'm going to execute the action in the world to get my next state. I'll sample my next action. I'll run it in the world to get my next state. So you just sample a trajectory sequentially, right? So that's how you get data. So you can get trajectories that way. So you can get S naught, A naught, S1, A1, all the way till ST, right? Now for each of those state action pairs in your trajectory, you can like, your policy, which means that you can stick in S and get what the likelihood of A is going to be, right? So imagine that your policy was a Gaussian, let's say, right? And let's say you stuck in S and it gave you some mean and covariance. Let's say it gave you some mean and some covariance, right? And then you have some action A that was actually executed, and so you can compute its likelihood, right? And now what you're going to do is, but you're doing this with PyTorch, and so you like know what the functional dependence is, so you can compute the gradient of this thing with respect to theta, right? And so you're going to compute the gradient of this thing with respect to theta, and then you take the sum of rewards along your whole trajectory, multiply it with the gradients that you get from PyTorch, right? And that's going to give you the gradient to move your whole policy in, right? Yeah, yeah. So it's a little confusing, but like whenever you have like a Gaussian distribution or something, you can always compute pi theta or log pi theta. And so like for instance, let's say you have a Gaussian, right? So you'll often have something like this. Um, x minus mu theta, the whole square by sigma square, something like this, right? And so like this expression is the likelihood. You can take the log of this expression, but essentially mu theta depends on theta, sigma theta depends on theta, right? So this expression is inherently dependent on theta, so you can compute its gradient, right? And so you can do this for the critical bit with the reason policy gradient is actually hard with diffusion models is because you don't know pi theta in diffusion models. And so it's easy to do with things like Gaussians or a mixture of Gaussians, but it's hard to do with things like diffusion models. And so that's what makes it hard. Um, yeah. You can even compute the gradient without the log. So like imagine that you have the expression from earlier, right? So like it's still a function of like these things are there's still a function of theta. So you can still compute its gradient. It's just a nasty gradient. It's a much nicer gradient with the log. Um, the thing that makes diffusion models hard to compute is that there's a nice closed form expression here for likelihood. So I can like do symbolic or auto differentiation to get the gradient with respect to theta, right? So like I can see that mu is a function of theta, like my neural net will output mu and my neural net will output sigma. Whereas in a diffusion model, nothing, I actually get this, I would get grad AT log phi theta AT given ST. Like to go from here to what grad theta of log pi theta would be is not that trivial, right? And so it's basically this thing doesn't ever give me a closed form expression for pi theta, which means I don't know its dependence on theta, right? And so that's what makes it hard to do with the diffusion. And so any function that gives you a closed form for pi theta is good. Good. Yeah, so there's a few ways that people have done it, right? One way that people have done it is you can actually, if you the diffusion model itself is not like something whose likelihood you can compute, but if you look at every step of a diffusion model, like so a diffusion model often will be at like xt, it'll do a step to xt minus one, it'll do a step to xt minus two, and each of these things is a Gaussian. And so what some people do is that they try and basically backpropagate through the whole diffusion chain. And that has while the whole diffusion model itself is not computable in a closed form, like each of these little steps is, right? And so then they treat these as like steps in your RL problem. And so then they like essentially try and adjust like each denoising step. That's one way people do it. The other way people do it is they try and do like supervised learning. And so they like they'll start from some actions, they'll improve those actions, and then they like do supervised learning with diffusion, right? And so they like try and convert into supervised learning. Good question. I can send out some references if you're interested. But it's like a underexplored kind of like upcoming area. Cool. So we have 2 minutes left. We're not going to get through the details here, but let me show you guys some videos before we end. So here's some we'll cover a few more advances on Wednesday. But these were some of the first examples of policy gradient in action. So there's an algorithm called TRPO. Um, John Schulman, you've probably heard of him, kind of came up with these, but you can get these strange creatures to walk in Mujoko with like just trial and error, which was amazing in 2050. They're kind of fun to watch. But you can get them to stand up and do cool things. But then they kind of took the same algorithm or a similar algorithm and applied it to um, StarCraft or Dota 2, one of those two. Is that Dota? Okay, good, good. Um, And so you can apply it to Dota 2. This basically very, very few changes. And then you can also apply it to robotics problems, right? So they had a cube rotation problem where you train in simulation and transfer to the real world using similar techniques. So essentially not that far from policy gradient. A few changes, but not that far. The same things are also used in LLMs. So you in LLMs, what you often do is you have preference data sets. You like train a reward model, and then you use that to do reinforcement learning with the policy gradient algorithms we talked about to like stamp out toxic outputs, right? And so it really improves the performance. Like if you look from GPT-3 to ChatGPT, like the big change is like RLHF. And then you can also, with a few changes, get it to work on real robots. And so here are some examples. So we have some examples of like learning to walk in around 20 minutes with RL in the real world. You can learn to do insertion tasks. You can learn to do cable routing and and tasks that are pretty hard in, see if I can forward. But basically in 20 minutes, you can learn how to walk. Um, so that's pretty awesome. All right. I'll see you guys on Wednesday. Thank you.